My name is Bob Dolan. I'm the CTO at Echelon Corporation, and I have my two colleagues here as well. And we're going to talk today about using the Raspberry Pi to prototype and create Internet of Things distributed applications. I'm going to talk a little bit about now what we think of as the Internet of Things communication models, requirements for an autonomous federation of peers. We think the Internet of Things requires peer-to-peer communication. I'm going to talk about a publisher-subscriber data model that we use to exchange data among these peers. Talk about how the network gets organized, and that's more than just assigning IP addresses, but it's also having nodes discover each other and what their services and capabilities are so that they can work together. And then talk about some work we've done with Python to make all the difficult problems of distributed computing a lot less visible to the developers so the developers can focus on their applications. And then we're going to talk about this demonstration hardware, what we brought, what it is, do a live demo of it, hopefully, although this is a show. And then finally talk about how you can get the SDK to do this. So all you'll need is some Raspberry Pis, you download our SDK, and you can play with this model as well. It's free of charge. So when we think of the Internet of Things, it's a huge application space, but like everything, it started out in one way and then progressed a little further. It started off as really an asset management kind of activity. And so it's sensors sending data up to a database and server machine. And that model got generalized as an asset management model to include things like, monitoring fleets of vehicles, or monitoring temperatures in storage containers on ships, or monitoring air quality or water quality, all kinds of things. But it's the same kind of situation where you have a bunch of sensors who are sending things up to a big database in the sky. So that client-server model is really well suited to using IP, because when we look at the internet is really a client-server computing system. Now, the industrial internet is the idea of using the internet protocols, but in a more of a distributed peer-to-peer communication model. So it's not just client-server. And that's needed for doing local and distributed control, where the devices talk to each other and make decisions. Sometimes they have to make decisions and react faster than any human could. So you couldn't have somebody sitting at a station watching things and be able to react. So it turns out IP protocols need extensions to handle things like multicasting and multicast security. And when we look at the direction of the Internet of Things, we see more and more people using more constrained devices that are limited in terms of their memory. They're on links that maybe are not as reliable as Ethernet, using low power wireless or things like that. So some of the communication problems are more difficult. When we look at the architecture of the industrial Internet of Things, we see a lot of different things. There could be a services platform in the cloud doing analytics and data gathering. Comes down to a local site where there's networking infrastructure, some devices connected on Ethernet, some on Wi-Fi, some on narrowband, low-power wireless, some on multi-drop wired communication or even power line communication. And so these systems tend to be multi-link. So the other day we made a big announcement about IZOT, which is our platform for the industrial internet. And the roots of that are, IIoT, eyes, OT. So we had to make it sound like something, and that's what we picked. But it's based on an open standard protocol with services added above the IP transport layer. So most people who are using IP with constrained devices are not using TCP. And the reason for that is TCP has got a lot of overhead associated with it, but it has a lot of great features. Things like being able to have acknowledgments and packet ordering and duplicate packet detection and all these other good things, whereas UDP does not. So most people who are using UDP for the Internet of Things then have to find ways of replicating those necessary services. The other thing about TCP is just to set up that connection, you have to send 3 unreliable messages. And if you have a link that is not as reliable as Ethernet, those 3 messages may not always get through. Finally, TCP being point-to-point only is difficult to do any kind of multicasting with. So in the industrial Internet of Things, every device is an equal peer. So devices can communicate with each other or with a group of devices. Groups can span multiple links. Links can be different physical media. And devices communicate using a notion we call data points. So data points are more than just a scalar value. They include things like a maximum and minimum, illegal values, and semantics. You know, it's not just a temperature, it's an outside temperature, or it's a flow, or whatever. And having this simple data model keeps device applications not having to be concerned about where the consumers of these data points are. They can be anywhere on the network. The device just updates the data point and it goes out to all the subscribers wherever they are. So here's an example of some data points. This is a simple heating system. It's got a set point, which is the temperature you want it to be. This is 23. This happens to be Celsius. It's not that cold. And then you have a temperature sensor that is sensing what the value is in the space being controlled. And then you have a heating system. And the heating system is running the control algorithm that is taking a look at the set point, comparing it to the current temperature, and deciding how much heat to apply to the space. So in IZOT, devices communicate in this way using data points. And a data point is a value that can be 1 to 228 bytes. And a device can have up to 4K data points. So you develop a sensor, you publish information that you are sensing. Subscribers pick that information up and use it however they want. So along with this, we have a bunch of standard data point types, and also people can extend the model and create their own data point types. So we have things like alarms and analog values and load control settings. And these standard data points with semantics facilitate communication among devices from diverse manufacturers. So the next thing is, if you have data points, all these nodes, they came from all over the place, they all can produce or consume data points, then you have to connect them up. You know, you can imagine a lighting system might only have 2 kinds of nodes. It has lights and switches. So how the system behaves depends a lot on which switch controls which light or group of lights. And so these connections, in a way, form a lot of the distributed application. So in our model, data points can be connected either by a network installation tool or by the devices themselves. And we're going to be demonstrating the devices themselves doing it without any other tool. And the tools or devices themselves can then confirm that the data point types that are being advertised are compatible with their inputs. So when we go and see what has to happen, well, if you want to send a data point, you might need to absolutely know that it got there and when it got there. So we have an acknowledge service for that. So the sending device updates a data point. It goes out over the network. Timers are started waiting for an acknowledgement. When the acknowledgement comes back, that transaction is considered complete. If the acknowledgement doesn't come back after a timer goes on, you retry, and if you exhaust all the retries without the acknowledgement coming back, then there's an error logged. That's reliable delivery. And request response is the same way, only you're getting data back. So there's other message delivery services like to send an unacknowledged message, just send it out once and hope it gets there. And you might say, well, that doesn't sound very reliable. But if you're doing something like implementing a time server, where you're sending time out periodically and fairly frequently, and all the nodes who are receiving that can run free and be accurate for a certain amount of time, it doesn't really matter if they lose an update every now and then. Then there's repeated service, where you can send a message in rapid succession several times that's unacknowledged, with the idea that each time there's a probability of error, but if you send it multiple times, then the probability becomes quite small. So I'm going to turn this over to my colleague now, who's going to talk about the installation service. This is Rich Blumseth again. But I want to preface all these remarks by saying we're telling you about what's happening underneath in this presentation. But then when we show you the Python classes and what's going on, you're going to see that you as a developer don't have to be concerned with any of these things. So Rich, go ahead.
Okay, thanks, Bob. So Bob introduced a little bit about about the ISI protocol, but I'll talk a bit more about it. So ISI is interoperable self-installation. It's a technique that we've developed that runs on top of IP that allows IP devices to automatically discover each other and automatically exchange data between each other. And we have some key concepts that enable that to happen. They're called fire and forget, bandwidth control, support for network growth, and a very flexible connection model. So I'll go into a little bit more details on those. So fire and forget. A typical managed system uses a central server to assign addresses within the system to allow the devices within the system to talk to each other. So when your PC talks to your printer, there's often some central authority that assigned those addresses and made that happen. The idea of fire and forget is that we want devices to be able to assign their own resources. We want a device to be able to assign its own address and also assign its own information on how it's going to communicate data with other devices. Because what we're creating with this system is a peer-to-peer system where devices talk to each other. So to talk to each other, they have to know each other's addresses. And those addresses have to be unique within the network. And so we want to do that without having a central authority to assign that. So we use a patented algorithm that we call fire and forget, where when a new device has a resource, so for example, like in here I have a keypad that could talk to a number of lights. And I want the lights to announce themselves to the network saying, I'm a light sitting on the network, someone can connect to me. But that light that's going to make that announcement has to have a unique address for that little piece of information. And so the way it gets that unique address is it just picks one randomly. So it doesn't go to some central server. There's no special DHCP server or anything like that. The device picks the resource itself. It picks an ID, and it just broadcasts that information saying, I'm using this address. And the device assumes it's unique at that point. Now, since it is random, it's not necessarily unique, but it assumes it's unique. And it periodically then informs other devices that it's picked this address. It's saying, I'm using this address, and just letting you know. So if another device in step 4 here, if another device sees that there's a conflict, it sees that, oh, this device picked a resource that I'm already using, that other device changes. So there's never sort of a request response required. Right? The devices just pick their own addresses, broadcast that information. When a conflict occurs, the conflict gets resolved at the other end, not at the end where the resource was picked. So that gives us a way then to allocate network addresses within the network and to allocate connection information so that devices can talk to each other using unique identifiers for the data they exchange and picking those identifiers dynamically and in real time. Now, second key part of ISI is the connection model. So how do these devices talk to each other? And devices may have multiple bits of information. So as an example here, I have lamp controllers that are controlling 3-color LED RGB lights. And so these lamp controllers have a data input which says, set the color to red or set it to violet. Right? But they also have outputs that say, well, I'm currently using 3 watts of power. And I'm also reporting how much energy is being used over time. So this month I've used 500 watts of power, right? Or 500 watt hours, sorry. So there's multiple pieces of information that each of these devices may want to expose or receive. And so what we do is we take that information and we collect it together into what we call assemblies, which are just groups of information. So you might have an assembly that is my color input, my power output, my energy output. And when the lamp gets plugged into the network, it just broadcasts the fact that, hey, I've got this information. If you want it, or if you want to send information to me, you can do that. So each device, each unique device then within the network can have up to 254 of these assemblies. So you may want to choose to break them apart. So for example, for the lamp, we could say I've got a lamp input that's going to set the color of the lamp and turn it on or off. But it may have an energy output, a power output. So those can be separate assemblies. So you have a choice as a developer, do you combine things, do you separate them? And you see sort of 3 examples in the diagram. So the first one is just very simple, just an output value. That could be the power output from the light, for example. Right? Or it could be a closed loop sensor. So a closed loop sensor is something that both receives an input and produces an output. And we have an example of that here with the occupancy sensor. Right? So we have 2 occupancy sensors on this board on 2 different devices. So each one is sensing local occupancy, saying, oh, I see occupancy there. But envision that they were in 2 ends of the room. And so at one end of the room, the sensor sees that the room is occupied at that end. The other one doesn't see that. But the two sensors could be tied together. So the outputs of the two go to the inputs of the two. So the other sensor would not only be able to sense physical presence, that there's somebody over there, but get data from this device saying, oh, there's actually someone in the room just at the other end where I can't see it. So that's a closed loop sensor where you have inputs and outputs. And that's a good assembly. The assembly combines that input and output into sort of one unique thing to offer to the network. So the occupancy sensor offers that to the other occupancy sensor, and they can exchange data. And assemblies can be more complicated. And so the complex one at the end is what I described with the lamp, if you combined the lamp control with the power output with the energy output. All right, so these connections are great. These connections allow us to have peer-to-peer connectivity between devices. My keypads can control my lights. My occupancy sensors can control the lights. I also have a humidity sensor, temperature sensor, light level sensor that reports that information. And so, for example, the light level sensor can report how much light is in this room, and the lights can use that to make decisions as to how bright they should go. Right? So if I have lots of sunlight coming in, they can dim down. When there's not much sunlight, they get brighter. So that's from the lux sensor telling the lights. So we have all this data we want to exchange between devices in a peer-to-peer network, again with no central controller at all. But how do we find each other? How do we find the connections? How do we get this keypad connected to these lights, or that occupancy sensor connected to the lights? So we have three methods. So the first method is manual. So manual is very simple. We define something called a connect button, and I'll show a little scenario how the connect button works. But with the connect button, I can just simply go to one of the devices, say a keypad, push a button says connect, go to the light, push a button says connect, go back to the keypad, say confirm that, and they start talking to each other. Again, just by exchanging data with each other, there's no other central authority involved. And so that's really nice for these kinds of networks, like where you have keypads and lights and you want to be able to just easily connect them together. So a user can do that, and there's no other tool required, right? So the only tool is the finger and the button on the lights and keypad. Another type of connection is automatic. Maybe I just want devices to discover each other automatically. So a good example of that would be like these temperature sensors, the humidity sensors. I'd like those to just broadcast the fact that they have this information, and anybody who wants it can get it. And the user doesn't really want to get involved with pushing buttons on the temperature sensor. He doesn't care. He just wants the temperature to get reported. So in that case, we have automatic connections where devices can just announce the availability of information, and other devices can automatically just connect to it with no other involvement from the user. And you can combine these two, and that's what we do in the scenario here, where at first we just plug these things in and they just all start talking to each other. And for a small system, that's what you would want. But a bigger system, you may have multiple rooms. You may have one room with its keypad and lights, and you have another room with its keypad and lights, and you want those to be treated as two separate networks. So in that case, you don't want it to be fully automatic. In that case, you want to use the manual connections to get everything associated correctly. Finally, we have controlled enrollment. So controlled enrollment is, well, maybe I don't really want to wander around the building pushing all these buttons. Maybe I'd rather just sit down in front of a web page and connect things together. So with controlled enrollment, you can do that. You can display a web page to your user. It says, here's all your devices. What do you want to connect? And you pick from those devices and you just say, connect them. What the web page actually really does is virtually push those same buttons, right? The web page talks to the devices and says, hey, push your connect button. And so it's as if you wandered around and pushed all the buttons, but you can just sit down in one place and do it all. So that's the three models, and an individual device can support all three. So let's look at an example of that first case. So the first case is manual enrollment. How do we really make these devices talk to each other? And how can we do this in an IP network in such a simple fashion? So I'm going to show an example here with three devices. I have a closed loop sensor. So envision that's my keypad here. So the keypad is a thing that will allow the user to push a button on the wall and send out a message to all the devices in the room about what state the user wants. And on the right are closed loop actuators. And so an example of that would be the lamps. All right, so lamps that take an input for what scene should I be in, or what level should I be at, or what color should I be at. Right? So if I want to create a manual connection, I can go to one of these devices, like the closed loop sensor, and push the button. Right. What happens when I push that button is, first thing is that device, say the keypad, sends out a message called an open enrollment message. So that message tells all the other devices in the network, hey, I've got this information, happens to be what I call load control information. and if you're interested in it, let me know. Right? So that message gets broadcast to all the other devices, and the user is informed by simple LEDs on the devices. So we call this the connect light. So there's a connect light on each device. So when the user pushes the button, they see the light flashing on the device where they push the button, but they also see the light flash and all the other devices that know how to talk to that. So, if I have a blender that doesn't know how to talk to a keypad, the blender doesn't start flashing. But the lights, yeah, they know how to talk to keypads, so they start flashing. So now the user goes to the second device and pushes the connect button there. That tells that device, yeah, go ahead and make that connection. I can see you know how to do it because your light was flashing. So he pushes the button, the light goes solid. So solid means, okay, we'll join that connection. And notice how it went solid also on the sensor. That's because the actuator sent back a message to the sensor saying, yeah, I accept your enrollment offer. It's a good deal, so I'll take it. And so the light stopped flashing saying, okay, we have a potential enrollment already set up. Those devices are prepared to talk to each other. They don't quite yet, but about. The third device doesn't yet, right? So we go to the third device, push the button there. That sends back an acceptance as well. So now we have two acceptance. And so we have two devices that have said, yeah, we're interested in that data from that keypad. We go back to the keypad and push the button one more time, said, yeah, let's make that happen. So you push the button one more time, the keypad sends out a message saying, it's a connection status information message saying, yep, make that connection. It's a good connection, let's do it. All the devices turn the lights off saying, we've done it. But now at this point, they're all connected. See the line there in the middle. So when the keypad has a new output, the user pushes a scene button saying, go to my movie scene. The scene goes out on the wire, but it only goes to those other two devices. They receive the message and they go to that new scene. Right? And so that's the entire installation scenario. So that's how we do installation, is with ISI. But now we want to create devices. Right? We want to create devices like these that talk to each other. And so we want to have a simple way to create those applications. Right? So what I've talked about so far is really more of the protocol. How do these things talk to each other? What can you do? How can you exchange data? So we have this great protocol, this great connection methodology, but we also want a very simple way to create the applications that run in these devices. And the simple way that we've come up with is based on Python. We use Python 3. And what we've done is created Python classes that hide a lot of the complexity of the protocol, right? And hide the complexity of what's happening under the covers. Because as Bob described, there's a lot that you want a protocol to do for you to provide reliable delivery and to provide this peer-to-peer connectivity and to make this all simple. But we want to make it simple for the developers as well. So what we do is we create Python classes that encapsulate that complexity and allow you to write Python applications with just a few lines of code that actually implement this sort of connectivity. So here's an example of the code you would write to implement a sensor. So a sensor could be something like my temperature sensor here, or my humidity sensor, my occupancy sensor, the keypad. Those are all sensors. They all take some kind of physical world input. So I've got a physical input. Now I want to make that data available to other devices on the network, because that's what the peer-to-peer networking is about. And so what we do within our Python classes is we provide a very rich set of resources that define the kind of data that you might want to exchange and how that data gets organized. And we have hundreds of these resources. So the resources are things like data point types. So a data point type might be a load control value, for example. How do you control the level of a light? How does a keypad report its state when the user pushes a button? But it may also be a simple analog input. All right, and so an analog input is something like a temperature value, a humidity value, a light level value. So those are all defined in standard resources that come with our Python classes, so you don't have to invent all those. You can invent new ones if you want, but we give you hundreds to start with. And so in this example, I'm going to use one we call the IoT analog input. So that's a good profile to use for any kind of sensor device that's sensing some real-world piece of data. Right? And it is a profile. What a profile means is it's a collection of inputs and outputs and configuration information. Right? So the IoT analog input profile defines how a sensor device would report its sensed data. Right? So it's got a simple value output, of course, but it also has lots of configuration information things like alarm set points. If I have a temperature sensor that's sensing temperature, I want to be able to say, well, if the temperature goes over 200 degrees, that should be an alarm. So that's called a property that configures that profile, and that's defined by the profile. Right? So just by referencing the profile, which I do with that one line, I import that profile. Actually, I have that definition now available to my application, so I don't have to create all that. Right? I just have one line of code. I then actually want to create what we call a block. And a block is just an implementation of a profile. Right? So the analog input defines a generic analog input, but my block is one particular instance of that profile that runs on my device. Right? So my temperature sensor down here, right? I want to be able to create then an analog input on my sensor. That becomes a block. So to create the block, again, one line of code. I just say temperature sensor equals app.block, refer to the analog input, and I give it a name. I'm going to call it temperature because it's going to report temperature. So with that, I've now created a block then that implements that profile. And finally, I want to actually send out my temperature value, right? So I've got some intermediate code that ... that's my actual physical code, right? I physically go out and read temperature from the temperature sensor. So in this example device here, for example, I have a DHT22 temperature sensor connected to a Raspberry Pi. And this code, I have code in there that can read that sensor. Once it reads its value, though, I need one line of code to publish that value on the network. So that one line at the right side is the temperature that I've read from the physical sensor. On the left side is the data point I want to publish those other devices. So any other devices that I'm connected to through those methods I talked about will receive this value. So when I say present value equals float temperature, present value gets updated with that information, and that's all the code that's required from the programmer. And of course, under the covers, a lot happens within the script and within the protocol. But you don't have to write lots of complex code to make that happen. So what we announced this week at Echelon are two stack products. So by stack products, we mean you can take these products and incorporate them into your products to create your own devices. So these are just software products, software that you can freely download from our website, and I'll talk at the end how you can get the software. We have two stacks. So one we call the device stack. That's for creating devices like these that just talk to each other, can share data on a peer-to-peer network. And then we also have a server stack. And the server stack is used in the center device here, but you create your own servers. And the server is the thing that can collect data from all the devices on a network and expose it through a very simple REST API. And using that REST API, you can create web pages or other kinds of web applications that interact with your networks. And again, both stacks are free downloads today. It's beta software, but free beta software. The stacks are both written in a combination of C, C++, and Python. And we provide sample applications and sample web pages that run on a Raspberry Pi. So that's what we have here. This is actually a board that has 6 Raspberry Pis on the board. 5 of the Raspberry Pis are running the device stack and doing some kind of local control, either a local sensor or a local actuator. One of them is running the server stack to be able to host web pages. And with the device stack, you can actually develop either in Python or C and C++, though with Python we make it much easier because it encapsulates more of the complexity for you. But that's all running on top of our control services layer that implements all the services that Bob talked about, things like reliable message delivery and the other additional services you need on top of IP to really create a reliable control network. And all that then runs on top of Linux running on the Raspberry Pi. On the right side, within the web server, within our server stack, we have a web server that sits on top of our REST server. So our REST server provides this very easy to use RESTful API that makes it simple to discover devices, to talk to data points, to read data points from either a web page or from your own web applications. That in turn is sitting on top of a network server that actually goes out and discovers devices and maintains a database of all the devices, all the data points. So when your web page requests a data point, it gets it from the network server. And that in turn is also running on top of our control services. Now, as I mentioned, the stacks also come with example code. Excuse me. So there's a reference implementation of the stacks that runs on a Raspberry Pi. So we provide the stacks and source code if you want to port to another platform of your choice. but we also have the reference implementation that runs out of the box on a Raspberry Pi. And the stacks come with example software. And this is what the example software does, and is also what I'm showing here. So this is the same examples that I'm showing here that come with the product. And again, these all come as free source code, free schematics. So we have 3 sample devices shown here. So on the top is what we call the environment sensor. So the environment sensor uses Adafruit modules, because we like the Adafruit modules, they're really easy to work with. So it has an Adafruit light level sensor, a passive infrared sensor for doing occupancy, and a temperature and humidity sensor. So we interface those 3 devices to the Pi directly. The second device is what I'm referring to as the keypad. The keypad you see down there in the middle. So the keypad has a display like that, which are little touch push buttons, right, where you can select a scene for lights in a room. You can make the lights brighter, dimmer. You can change the color of the lights just by pushing the hue buttons. Or you can just turn everything on and off. Right? So that's all done with a little 2.5-inch touchscreen display. We've interfaced the touchscreen display, again, directly to a Raspberry Pi, and then control it through the Python package that I described. And finally, at the bottom are our color LEDs. So these are 3-watt RGB LEDs. They're from Solar Robotics. So we have 2 per Pi. We use a 16-channel PWM, also from Adafruit, to control the level of what's really 6 LEDs, right? Because there's 1 each for RG and B. Right? So that's the 3 example applications we deliver with the device stack and that we're showing here. In the middle is an IZOT server, right? So the IZOT server is running the server stack, right? So the IZOT server is monitoring this network that you create, and you can have lots of these if you want. You have lots of sensors if you wanted, lots of LEDs, lots of keypads, right? And that can all get monitored by the server. The server is collecting all the data from all of those and making it available through the RESTful API. And then we provide sample web pages that you see there on the right. So the sample web pages allow you to do a variety of things. The top one we call the dashboard. So the dashboard is sort of tailored to this set of examples. Right? But the dashboard kind of shows you energy usage from the LEDs. It shows you, temperature and humidity and light level from the environment sensors. Shows you the state of the LEDs. You see that on the top right, the little circles. That's the state of each of the LEDs that it's discovered. And this is actually all built dynamically, right? So if I had more LEDs, you would see more circles there. And you can click on one of those LEDs and it turns it on or off, depending on its state. And the second page, we call that the LEDs page. And on that one, we can actually control color with a nice little color picker. You see the circle there, where I can pick a set of LEDs on the bottom, put little check boxes next to the ones I want to control, or pick a keypad to relay the information through a keypad. Click on the color picker, and all the LEDs that I've selected go to that color. And finally, the bottom's a charts page, right? Because often for the Internet of Things, you want to collect data from sensors and show that data over time. So the charts page shows you an example of that, where I can pick an environment sensor and then see how the temperature and light level and humidity change over time. So that's the hardware's running here, but also the hardware and software and web pages that all come with our freely available kits. You can get our kit. You can program the software into Raspberry Pis, get them up and running. You don't have to use a Pi, but a Pi is a nice way to get started. Use ISI to organize your network to get the devices to talk to each other. You can test your networks, interact with them through the RESTful API. You can start with our example web pages, but you can create your own web pages. And we really encourage you to try this at home. And it's all, as I said, it's a free download. Here's the link. Just go to iiot.echelon.com/getstarted. And from that link, you can get our package. That'll come as a single archive file that you can copy to your Raspberry Pi. And then on the Getting Started page within our documentation, you can actually see how to install it and get it running and start developing. So then all you need is get some Raspberry Pis, and they cost $35 each. They're not too expensive. Right? Get whatever I/O you would like. As I said, we use a lot of Adafruit modules for our development, prototyping, and demo development, but you can use whatever I/O you would like. You can create your devices with your I/O and then create some cool web pages that interact with those devices using our RESTful API, and then you can really impress your friends with how you got all your Pis to talk to each other and talk to the web. So with that, I'll open the floor up to any questions. Yes?
So how are the individual modules identified? You said that they self-organize, they get an address,
Mhm.
and then if somebody else comes on, they pick an address, and if it happens to be a collision, something that you've identified and are communicating with all of a sudden has a new address.
Mm-hmm.
How do you know that that sensor didn't move to the other side of the room?
Okay, yeah, I'll repeat the question in case you didn't hear it. So the question is, say I have some sensors that are communicating with some other devices, they're exchanging data, right? But I said that another sensor could come onto the network and it may pick a duplicate address, and the first one would change it. So the way that happens is there's a unique identifier, another unique identifier created for a connection that truly is unique, kind of a globally unique identifier that's created for a connection that's managed by what we call a connection host. So when there's multiple devices connected, one of those devices is a connection host. In my diagram with the push buttons, it was that first one I pressed became the connection host. So it created a globally unique identifier as well as the smaller identifier that's typically used. And that globally unique identifier is actually sent from the connection host to all of everybody it's connected to. All right. And so when it changes the short address, the other devices it's connected to find out about that because they say, oh, my connection ID just got changed to this new ID, and they just changed. So basically they all change together. So that the whole little sub-community will move to a new address. Other questions? Yes?
How do devices advertise their functions? I mean, these are web services, basically, right? And how do you know it's a temperature sensor that you're receiving?
So the question is, how do devices advertise their functions, and are these really web services? They're not really web services, right? We have this sort of simpler data point model and data points implemented within profiles, right? And the profiles have standard definitions, like I showed the IoT analog input profile, right? So that profile has a unique number as well, right? And so when the device advertises what it is, or what it has, like my temperature sensor says I have a temperature value, it actually says I have a temperature value and I implement the analog input profile. So all the other devices say, oh, that guy's an analog input. So that's how they know.
You have to define a new device. If you create a new kind of device,
Mm-hmm.
you have to add this to.
Right, so that's why we have this concept of standard profiles and custom profiles, right? So if you use one of our standard profiles like analog input, everybody else will know what you are, right? If you define some entirely new thing, the world's best galactic blender, you could create your own profile for that, but no one else will know how to talk to you, right? But you could create multiple devices. What?
You'd have to put that new profile on every device that you wanted to be aware of.
Exactly. So if you're creating the two devices that are talk to each other, you can create some brand new profile for those two. And since you program both ends, this end would say, I'm your blender, and this guy would know how to talk to your blender, and that would all work. Other questions? Okay, well, thank you. So we'll be around for a few minutes afterwards if you want to come up and ask some more questions or see our cool little pies up here. Thanks.